Hello everyone. So this is my first video where I'm actually going to teach something. It's on real analysis by Walter Rudin. I've read this book to some extent so far, and I want to give you a lesson on chapter one. So I now share my screen. I made a little something so I can show you. Okay, I wrote this on LaTeX. So as an introduction, this first chapter is about the real and complex number systems, starting with numbers, their basics, the real number system, and it motivates the construction of the real number system. So we start by proving that there's no rational number p in Q such that p squared equals 2. So suppose for contradiction that p equals m over n is a rational number in lowest terms such that p squared equals 2. Then m over m squared equals 2 and m squared equals 2n squared. Thus, n squared is even because it's a multiple of 2. It's 2 times n squared. The 2 makes it even. And we let m equals 2k because it's even. So we get 2k squared equals 2n squared. So we get 4k squared equals 2n squared. And we get n squared equals 2k squared. And notice here, we're taking this m over n, these m and n, so that's their greatest common divisor is 1. But here you see that n squared is also even, which contradicts that m over n is in lowest terms because m and n are both even. And to further emphasize on this, if you take this set of all rational numbers such that p squared is less than 2, instead of all rational numbers such that p squared is greater than 2, uh, uh, we let this set be a and this set be b. Basically what we do is we claim that A has no largest number and B has no smallest number. And to do this, for any p greater than 0 in Q, we define Q equals p squared plus 2 over 2p, and we get Q minus p equals this, and Q squared equals this. Now, let's read what this says here. If p is an A, then p squared is less than 2. Okay. Because that's the definition of A, and Q is greater than P. Why? Because Q greater than P is basically the same thing as Q minus P greater than 0. So we want to see if this is greater than 0, which it is, because if you set this greater than 0 and multiply 2P on both sides, get 2 minus P squared is greater than 0, which means P squared is less than 2, which is basically this fact. So we can reverse engineer our way to get this statement. And likewise, we get Q squared is less than 2 because let me think of this a little second. Yes, I remember. Okay. I'm going to introduce something a little bit more advanced here. I'm just going to go forward a little bit to introduce some ideas so I can bring it there. Let me just find it. Okay, we'll see it later anyways. So basically, we can just, because if something is less than something, we can multiply the same thing on both sides if it's positive and get the same result. So that's what we're doing here. We get t squared is less than q squared. Sorry, q squared is greater than p squared. So q squared is less than 2. And therefore q is an A. Wait a second, just let me think about this a little bit more. Yeah, that's sort of the logic here. So if p is in b, p squared is greater than 2, and likewise we get q less than p, and q squared is greater than 2 if we use the same logic. Hmm. And we get q is in b. Thus, neither A has the largest member nor B has the smallest. So this demonstrates that there are gaps in the real number system. Here we introduce the idea of sets, elements, empty set, non-empty sets, proper subsets, which I think are taken for granted. And order sets, an order on set S is a relation that is such that one of the following is true and there's transitivity in it. And there exists b if there exists b in S and x is less than or equal to b for all x in E, then we say it's bounded above, and b is an upper bound of E. And likewise, if it's greater than, it says we say it's bounded below or lower bound. And the least upper bound or supremum of E is if A is an upper bound of E and y is less than A, then y is not an upper bound of E. So this second statement here is saying that we're taking all the candidates for an upper bound and we're seeing which one satisfies this, that beats all the others, to make it become the least upper bound. And similarly, the great lower bound or infimum is denoted infimum of E. So let A and B be as defined in example 1.1. A is bounded above in Q and has no least upper. Okay, yeah. So we're talking about the first example here. Remember, it had a gap. There was no least upper bound or great lower bound, because that's what we concluded here. We said there was a gap. Neither A has the largest member nor B has the smallest, which is the conclusion we got. And here, we said let E1 equals all the rational numbers less than 0, and E2 would be all the rational numbers less than 0, including 0. See that the supremum of them is 0, but one has 0 in them and one doesn't have 0. So it's not necessarily a condition that the supremum or the infimum is part of the set. And if we define this set over here, the supremum of E is 1 because 1 over n, the largest it can be with natural numbers, is 1. And the infimum is 0, but it's not in the set because that's when it tends to infinity. An ordered set S has the least upper bound property if whenever E is in S, E is non-empty and bounded above, then supremum of E exists in S. Okay, now we have bounds and field structure. Theorem 3. Suppose S is an unordered set with the least upper bound property. Let B be a subset of S, be non-empty and bounded below. Let L be all the set of all lower bounds of B. Then A equals alpha, actually, but I'm saying A because it's easier. A equals supremum of L exists in S, and A equals infimum of B. In particular, infimum of B exists in S. Okay, let's read the proof. Since B is bounded below, L is non-empty. Why? Because it has lower bounds, and basically L is the set of all lower bounds, so it's not empty by definition. Every element X and B is an upper bound for L, because L is lower bounds, B is upper bounds, is an upper bound for L because L is basically what precedes B. So L is bounded above by the least upper bound property. Supremum of L exists. Call it alpha. If Y is less than A, then by definition 1.8, least upper Y is not in the set of upper bounds of L. Because alpha is the lowest, least upper bound. So if it's less than the least upper bound, so it can't be an upper bound. So y is not in B. Thus, a is less than or equal to x. Alpha is less than or equal to x for all x in B, which means alpha is in L. Exactly. Okay. Now suppose B is greater than A. Then B is not an L because alpha is an upper bound of L. Because if we look here, we said alpha is supreme of L, which is in the upper bound of L. Yes, an upper bound of L, and since it's greater than the upper bound, then that means it's not in L. Hence, B is not a lower bound of B. Because it's not an upper bound of L, if you understand what I mean. Therefore, alpha is the greatest lower bound of B, and we get alpha equals infimum of B. And here we have the axioms for fields, for addition, for multiplication, the distributive law, the notations used, the consequences of the field axiom. We get the cancellation law, the uniqueness of additive identity, uniqueness of additive inverse. And if you want to prove this, it's really simple. The strategy is using this linking factor, negative x plus x. Take 0 as this and this. Then you break this link and you make this link into this link, if you see what I mean. See, this is what it does in x. And x plus y equals x plus z. And we bring back the link to negative x plus x. So this is 0. We get y equals z at the end. If you put z equals 0 in A, we get B. And if you put z equals negative x in A, we get C. And if we apply C with negative x in place of x, since negative x plus x equals 0, we have negative x equals x. And we have the following axioms for multiplication. The following properties for multiplicative laws with axioms. We get if x is not equal to 0, xy equals xz. This is what I wanted to show, because here in the first part, here to get this, sorry, yeah, to get q squares, p squared is less than q squared. That's what we needed to do. Then we can use this property over here. Okay. If x is not 0, then xy equals x, then y equals 1. Okay, so I have to do a second round of recordings because it's cut. Okay. So we're talking about these over here. Now, the proofs are omitted here because they're closely resemble those in proposition 1.14. Further consequences of the field axiom: 0 times x equals 0. If x is not 0 and y not 0, then x are not 0. Negative xy equals negative xy equals x negative y, and negative x negative y equals xy. Here we can just say 0x plus 0x with the distributive law 0 plus 0x, which is 0x. And that means 0x plus 0x equals 0x. If you look, we have two 0x's here, one 0x over here. That means the other term is 0, because 0x equals 0. Now suppose xy is not 0 and xy equals 0. Then we can use this with multiplicative inverses. And we know xy is 0. So we know this is 1, but we know this is 0. So that doesn't make sense as a contradiction. So that means if xy not 0, then xy is also not 0. And here, negative x times y plus y is the same thing under the distributive law. Negative x plus x times y, which is 0 times y, which is 0, which means negative x times y, if you bring it to the other side, is the same thing as negative x times y. And switching orders with, instead of taking x as negative x, take y as negative y, we get this thing over here. And if we do negative x times negative y, we apply it to the same rule over here. And we get that is equal to xy. An ordered field is a field F equipped with, let me just see if it's recording. Yep. An ordered field F is a field F equipped with an order satisfying y less than z, then x plus y is less than x plus z, and if x greater than 0 and y greater than 0, then xy greater than 0. In an ordered field, we refer to x greater than 0 as positive and x less than 0 as negative. Rational numbers Q form an ordered field. In every ordered field, the following hold. If x is greater than 0, then negative x is less than 0. If x is greater than 0, and y is less than z, xy less than xz, and etc. If we see the proof over here, if x is greater than 0, then 0 equals negative x plus x, which is greater than negative x plus 0, because we know that x is greater than 0. So that means that's negative x is less than 0. And if we reverse it, we get that x is less than 0. If we no, sorry, if you want to get the results reversed, we can just start with x less than 0 and get negative x is greater than 0. Now, z minus y greater than 0, we get x times z minus y is greater than 0 because both are positive. And then xz equals xz minus y plus xy, which is greater than xy, because we're adding a non-negative term, because we know z minus y is greater than 0. So that means xz is greater than xy, which is what we get here. And a similar process for this one over here for C. And for D, if x is greater than 0, then x squared is greater than 0. We can just replace it, this over here, with, we can say y equals 0 and z equals x. And we get x squared is greater than 0. Basically, that's what we're doing. And if we do the inverse, we get this one. Since x is less than y and both are greater than 0, reciprocal inverse is 1 over y is less than 1 over x. Because if you multiply this over here by 1 over y, we get 0 is less than xy is less than x over y is less than 1. And you can no, just divide everything by 1 over xy, right? Basically what I'm trying to say is that it will give you this. It's going to give you the reciprocals is less than the other. Yeah. There exists an ordered field R which has the least upper bound property. Now we're talking about the real field. The field R is called the real number system, okay? Now we talk about the Archimedean property and root existence. The Archimedean property is the following. If x is greater than 0, then there exists a positive integer n such that nx is greater than y. And we get the following property thanks to it, which is the density of Q and R. If x is less than y, then there exists a rational number p in Q such that x is less than p less than y. Now, if we prove A, let set A equals the set of all the nx's with n in positive integers. Suppose no such n exists. That's our supposition. We're trying to bring it to the absurd. Then y is an upper bound of A. Why? Because basically, if no such n exists, that means this doesn't hold, and that means the limits of these n x's each time is going to approach y. So y is going to be the upper bound for a. By the least upper bound property, uh, gamma, or I'll just call it y again. Y equals supremum of a exists in R. Since x is greater than 0, y minus x is less than y, because uh, this you're basically subtracting on this side but not on this side, and if you look back at the axioms, this is going to yield that this is less than this, and y minus x is not an upper bound of a. Hence there exists m in the integers such that y minus x is less than mx, because y minus x is not an upper bound of a, so that means it's somewhere between the numbers in the set. That means there exists a integer m such that it's going to be like this. It's going to be greater. Mx is going to be greater than this. If we add x on both sides, that means we have y is less than or equal to m plus 1x in a, contradicting that y is an upper bound of a, because that means there's another element in a, because m plus 1 is also an integer, and this is greater than the upper bound, so it can't be a least upper bound. So sorry, it can't be a least upper, and it can't even be an normal upper bound. So since y minus x is greater than 0, sorry for the confusion here because this is alpha, and then so this is gamma. Since y minus x is greater than 0, part A gives n in the positive integers. Uh, yes, because we said that no such n exists. That means y is greater than x, so it means y minus x is greater than 0. Part A gives n in z such that ny minus x is greater than 1. Uh, yeah, right now we're proving the second statement. So now we've proved the Archimedean property, we're proving this. So we use our Archimedean property to get this, and then we expand to get this, and we let m1, m2, and z such that m1 is greater than nx and m2 is greater than negative nx by applying the Archimedean property twice. And like this, we get a bound like this over here. And we can say that there exists an m in z such that m2 is m minus 1. Actually, negative m2 is m minus 1. And m1 uh, is m in himself. Something along these lines. Which gives m minus 1 less than nx less than m less than ny. And if we divide n on each side, we get x less than m over n less than y. Which means that there exists a rational number p equals m over n, such that x is less than p less than y. Which means that the Archimedean property of R and part B states that Q is dense in R. That's what it means. Now, the existence of roots for every x greater than 0 in R and every positive integer n, there exists a union. Okay, I'm proving this statement over here. So the proof is as follows: if y1 is less than y2, then using the properties that we discussed earlier, we get y1 to the n is less than y2 over n, y2 to the n, and we let E equals this set, t greater than 0, t to the n is less than x. Now we know this set is non-empty since for 0 less than t less than 1, t to the n is less than t less than x. Why? Because if it's between 0 and 1, each time you're reducing by multiplying exponents, so we get t to the n is less than t. And since we know it's bounded by x, each exponent is bounded by x, we know that's also less than x. Also, E is bounded above by 1 plus x, since for t is greater than 1 plus x, we get t to the n is greater than t less than greater than x, because we know x is greater than 0, so 1 plus x is at least going to be 1. So if that means if we exponentiate it, t over n is going to be greater than t, and we know that it is going to be greater than x. Now we let y equals the supremum of e, this set. We claim y to the n is equal to x. Assume now we do like multiple assumptions here. Like here we do the assumption that y over y to the n is less than x, and here we do the assumption that y to the n is greater than x. So here we choose an edge h between 0 and 1 such that h is less than x minus y to the n divided by n times y plus 1 to the n minus 1. I have no clue which mathematician thought about this expression to simplify this proof. Like, I can imagine them sitting there maybe for hours thinking about which expression is a good expression so that I can bring this into the proof and it's going to be this, give me this precise results and I can use it. Like, it's crazy. Anyway, we use this. Let a equals y and b equals y plus h, and basically here what's the key point here is using this. If you, I'm going to show you. Uh, Let me search for the factorization real quick. Yeah, exactly. So, okay, I'm recording again because it gives me a limit. I hope it recorded that part I was talking about. Anyway, we just finished this part. The corollary over here is that ab to the power of 1 over n is equal to a to the power of 1 over n times b to the power of 1 over n. Now, we have a decimal representation of real numbers. Let x greater than 0 in R, define a sequence nk as follows. N0 be the largest integer such that n0 is less than x, and then choose n0 and 1 so that we get the decimal representation of x. And I defined each nk like this, and E as a set of these, and we get that x is equal to the supremum of this set, which gives the decimal representation of this number. And we have the extended real number names system with negative, infinity, and infinity. We get these results over here. And finally, we get the complex field. Basically, the same thing going on. Same addition is commutative, same properties a little bit than the real numbers. As you can see here, it's the same logic a little bit, but now we're dealing with two separate parts, a real part and an imaginary part. And you can do the algebra yourself. You can multiply both sides to see if it gives you the same thing. X, y is equals x times y times z. And here again, you can do the algebra to see that this gives you this. We define the complex number I. Okay, here's where it gets more interesting. We get these things over here, and yeah, this part. Let z doubly be in C, then the absolute value of z greater than 0, modulus z absolute value is equal to the z absolute value, etc., etc. If you prove it, z w squared equals ac minus b squared plus ad plus bc squared, which is the same thing as a squared plus b squared plus times c squared plus d squared. We're taking the different components and squaring them and adding them, which gives the same thing as multiplying them separately and squaring them. And if you take the square root on both sides, you get this. Now the real part of z is basically just a, which the absolute value of a, which is less than square root of a squared plus b squared. and we have the desired inequality. Let ZW modulus be ZW, Z plus W be Z modulus plus W modulus, and we get this over here, which equates to this. And we're just multiplying the real parts because uh, we're squaring things. And so we're going to get WZ modulus plus ZW modulus, which is going to equate to 2 real ZW modulus. And it's going to give us this thing, and this proves a triangle inequality. And now we prove the Schwarz inequality, which is this. We let A equals sum of AJ squared, B equals sum BJ squared, and C equals sum AJ BJ modulus. Then if B equals 0, then all the BJs must be 0. So C is also 0 because BJ is part of the C. And the inequality holds trivially. And we assume B is greater than 0, and we consider this expression. And if we can expand it, we get B squared sum AJ squared minus BC modulus sum AJ BJ modulus minus BC sum AJ modulus BJ plus C squared plus sum BJ squared. And basically the logic over here is that we're adding the modulus with the number itself, which should give you 2 times the real value, which is what we get here, 2bc. So we get this expression, which is simplified to this, which we can factorize to this expression. And we know that b is greater than 0, and this expression is also greater than 0. That means this is greater than 0, and it gives you this property over here, which is the Cauchy-Schwarz inequality. And we go into Euclidean spaces, these properties over here, and the metric space property, of course. Since all the terms are non-negative, this is greater than 0 as a proof for the first one. If x is greater than 0, if x is equal to 0, sorry, the modulus of x equals 0, that means xi equals 0 for all I, which means x equals 0. And ax, its norm is a squared times this, which gives you this. D is analogous to the Cauchy-Schwarz inequality we just did here. And for x plus y is less than, sorry, for x, yes, for x plus y is less than x plus y, get this here is the dot product of x plus y and x plus y, which gives you this. And we know the dot product is less than the norms multiplied, which gives you this, and takes square roots, you get this. And if you replace everything by x minus y, y minus z, and apply to E, we get the metric space inequality, which is basically the distance from x to z is less than or equal to this distance from x to y and to y to z. Now we get to the appendix, where we prove the construction of the real number line. Step 1 is the Dedekind cuts. A cut is defined as A in Q satisfying A is not empty. A is not equal to Q, and if P is an A, then Q is less than P, then Q is an A. And so basically, we're taking all the numbers less than P and making it like a subset. We're cutting the number line in half, basically, a little bit. A has no greatest element. If P is an A, then there exists R in A with P less than R. That's a third property. Okay. And if P is an A and Q not an A, that means P is less than Q. If R not an A and R is less than S, then S is not an A. We define A less than B if A is a subset of B and A is not equal to B. And it satisfies transitivity and trichotomy. So exactly one of A is less than B, A equals B, or B less than A holds. Now for the least upper bound property, we let A be a subset of R be a non-empty set of cuts. That is, there exists B in R such that A is less than or equal to B for every A in A. So this is like the ultimate cut, right? It contains the other ones. And we defined Y or gamma equals the the union of all of these cuts, and that means P is in the Y if and only if P is in A for some A in A, because it's the combination of all of these. Claim that Y is an R and Y is a cut, and that Y equals supremum of A. And we show the three properties of R, say non-empty and proper subset of Q. Since A is non-empty, choose A not in A, then A naught is not empty, and A naught is in Y, so Y is not equal to 0. So that means there's always something in Y. And for every A in A is a subset of B, and Y is a subset of B. So Y is not equal to Q. Yeah, okay. And downward closure, so suppose P is in Y and P is in A1 for some A1 in A. If Q is less than P, then by the cut property of A1, Q is an A1 is a subset of Y, so two holds. No greatest element, since P is in Y, P is in A1 for some A1 in A, and A1 has no greatest element. There exists R greater than P. I think these are self-explanatory. Now show that Y equals supremum of A. For each A in A is a subset of alpha, and A is less than or equal to alpha. Sorry, not alpha. A is a subset of gamma, and A is less than or equal to gamma. So Y is an upper bound of A. We already know it's an upper bound. So suppose that delta is an R is an upper bound of A with delta is less than Y. We want to see if it's really the least upper bound, right? Then there exists some S in Y such that S is not in delta. Because see, this is delta, this is Y. There's something in between such that S is not in delta, it's in Y. So that if it's in Y, that means one is in one of the A1s. That means it's part of A and it's part of some cut in A. But we just said the delta contains all of the cuts, or not, or actually no, and we just said the delta is the bound of all these cuts. So that doesn't make sense. So it's a contradiction. So that means Y is a supremum of A. And we define the sum of these cuts as R plus S for each R in A and S in B. So we're taking each element of these cuts and adding them together. And A plus B is a cut itself. It is non-empty because A and B are non-empty. It is not Q. Any sums of upper bounds of A, B lie outside of A, B. If P is equal to R plus S in A, B, then Q is less than P. Then Q is equal to R prime plus S. With R prime less than R, because we're taking something less than it and adding it to it, and we know Q is less than P. So that means R prime is an A, Q is an A plus B. If R is an A, then for some T greater than R, T is an A, so R plus S is less than T plus S is an element of A plus B. So that means the sum itself is part of A plus B. Commutativity, associativity, we get the same laws over here, and we also get the additive inverse. Now we get inequality preservation over here. Same thing as a normal number line, right? And get multiplication for positive cuts. It's basically the same thing, but now we're multiplying, and we define one as the cuts Q is less than 1. And for multiplication in all of R, we get these properties over here, which is analogous to what we saw earlier. We make a law, this distributive law example, let A is greater than 0, B less than 0, B plus Y greater than 0. Then if we if we define Y, because this is the same thing as Y, B plus Y minus B is the same thing. So AY is A times B plus Y plus A times negative B. A times B plus Y plus minus A times B. So if we take it on the other side, we get this. It's the same thing as a normal number line system. And now we get rational cuts. Basically, we find a rational cut as every number less than that rational number. So basically, we're taking these numbers to be sets and defining addition and multiplication over them to define what a real number really is, because the the rational number system has gaps, as we saw, but this one you can define other numbers in it too. So we get these properties: the cut of r plus cut of s is equal to cut of r plus s. Same thing over here. Now, if we want, okay, so there was this part we missed over here. So I'm just going to do it again. So this part, I want to say that if you look at this factorization over here and you simplify a little bit, you're going to get this, and you're going to get y plus h is to the n is less than x. So y plus h is an e. And if you look at the definition of the set over here, if you set t equals y plus h, that means y plus h is an e, which contradicts that y equals the supremum of e. And now we broke this proof into two parts: y to the n is less than x, and y to the n is greater than x. And we define k equals y to the n minus x over n y to the n minus 1. And we set for any t greater than y minus k, y to the n minus c to the n, y is less than y to the n minus y minus k to the n, because we just replace it over here and we take the inequality. And here, basically, just imagine a number here. So that number times n times y to the n minus 1 is less than y to the n minus x, which is basically what we're getting here. And it's actually going to be equal to y to the n minus x. And it's going to give you t to the n is greater than x if you cancel out these y to the n's over here. So that means t is greater than y minus k, and it's not an e because it's actually the inverse of e. Here it's supposed to be less than x, but here it's greater than x. Showing that y minus k is an upper bound of e, contradicting y is equal to the supremum of e. Hence, y to the n is equal to x. We get the following corollary for it. So ab greater than 0, you get ab to the 1 over n is equal to a to the 1 over n, and b times b to the 1 over n. And here's the proof. So that's pretty much it for this chapter. I hope you enjoyed it. This is my first video, so please consider liking, subscribing. I'm sorry if it had bad quality. I'm not sure if it had bad quality. I hope you enjoyed it. Thank you very much.